do number 54 here.
The density of nitrogen of 0.913 atmospheres is 1.07 grams per liter. Explain how this shows the formula of nitrogen is N2 rather than just N. So the density is equal to the mass over the volume. And the volume, this is for gas, so the volume of the gas is equal to, what is the volume of gas equal to? So we know that PV is equal to nRT, so we solve for volume. Volume is equal to nRT over P. So we'll just substitute that in here, nRT over P. Invert and multiply, and so that's the mass times the pressure divided by nRT. Mass over N, do you recognize that? M over N, the molar mass. M over N is called the molar mass, so we'll just do molar mass times P divided by RT. And so we can figure out what the molar mass is based on having this density here. In fact, we can come up with a molar mass equation as well. There are two ways we can come up with a molar mass equation. One is we could just rearrange the density equation, or two, we can derive it from scratch. If we rearrange the density equation, then the molar mass is equal to the density times RT divided by P. And so the way we can show the difference is the molar masses of these two are different. The molar mass of N2 is 28.02 grams per mole, whereas the molar mass for N is 14.01 grams per mole. And so based on what molar mass we come up with, we can tell if we get a molar mass of 28, it's nitrogen. If we get a molar mass of 14, it's atomic nitrogen. And so the density, we'll just plug in here, 1.07 grams per liter. R is 0.08206 liters times atmosphere per mole Kelvin. T is given in the problem 18 Celsius. 18 Celsius plus 273 would be 281. Is that right? 273 plus 18, 291, sorry. 291. Divided by P, the pressure they gave us is 0.913 atmosphere. It's just making sure the units cancel. Liters cancel out liters, atmospheres cancels out atmospheres, Kelvin cancels out Kelvin. The units I'm left with are grams per mole. So calculate the grams per mole. It's going to be 1.07 times 0.08206 times 291 divided by 0.913. Which gives us 27.98. grams per mole. 27.98, because there's going to be uncertainty. Or, maybe it wasn't so precise measuring the volumes and temperature or whatever else. So it's off a little bit, but which one is it closer to, N2 or N? N2. And so that means that the sample of nitrogen must be N2. It can't be N. The molar mass is way off.
Okay, are there other questions? Homework or? Anything else?
Do you have it like find subshells based on looking at the periodic table or every
The subshells. You kind of just memorize the way that it's organized here. So this first block here is the S subshell. And then the P subshell is in green here, the D subshell is here, and the F subshell is here. And so based on the periodic table, depending on where we are in terms of number, that'll tell us which subshell we're in here. So, it's just memorizing this. It would be numbered like this: 1, 2, 3, 4. Except the D's are offset. So 4 would be 3 here, and the D's 3, 4, 5, 6. And then the F's are offset here because we'd go 6S, 4F, 5D. That way. So they're offset. Just the D's and the F's. Otherwise, it's just like a row here. And this has to do with how the electrons are filled, what molecules are filling. So, you know, the periodic table forms the periodic table is just created from observations of chemical properties. And so the quantum mechanics theory here fits this. As you'd expect, that the theory should be a fundamental description of the observations. So the fundamental description of the periodic table is that it's organized based on orbitals and subshells. Does that answer the question? Or was there a specific one?
Or like, I guess, can you give an example of like writing the electron configuration for atoms?
Okay. We can use the periodic table to determine the electron configurations. It depends on which periodic table you use to figure it out. There are two types of periodic tables that you're going to see in here. And the different types are going to vary depending on what they do here in this region of the periodic table. So let's look at some different types. So you can see after barium, it drops down to lanthanum there. Take a look at what happened here. You see the difference? Look at this periodic table and look at this one. You see where they put lanthanum? Here, lanthanum's down here. In this one. We look at this one. Where's lanthanum? Above. Now, in the F, how many F orbitals are there? You know how many F orbitals are there? 7. There's 7 F orbitals. If you have 7 F orbitals, how many electrons?
4 electrons.
14 electrons can fill those orbitals. And so let's count these here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Can you cram 15 electrons into 7 f orbitals? No, there's something wrong here, right? And so this is the two styles of periodic tables. My preference is this, not this style. Otherwise, you get 15 in the bottom. They're not 15F. What they did was these are not F here. You know what these are? D. These belong up here, but they were cut here and then placed down here. Why? I don't know why. But I have a feeling that it's because people didn't like these little asterisks here and this little down. Do you see the double asterisks here? I have a feeling that people didn't like the double asterisks with this down arrow here. That's why. So in a way to make it simpler, they made it more confusing, I think, doing it this way, because it doesn't work. Now let's look. If we put lanthanum back up here, and then we use a single and double asterisk, then it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons will fill the 4f orbitals. There's 7 4f orbitals right here. Except what we have to do is there's a split here. You see that split? There's no split here because we go 39 to 40, but here there's a split because we're going to go 57 to 58. And so let's do cerium as an example. Cerium is 58 electrons, so we're going to use a noble gas. Xenon, we end at xenon with 54 electrons. So the 55th electron goes here, would be 6s1. 56th electron would be 6s2. 57th electron would be 6s2. This would be 3. We're offset by 1. 3, 4, 5. This would be 6s2, 5d1. That would be lanthanum, but we're going to cerium. So that would be, this is weird now. This is going to be 6s2, 5d1. Now this is offset. This is going to be 4f1. And so if I'm doing cerium, this is what I get. I would go back to xenon, which is 54 electrons, 6s2, 5d1, 4f1. Okay, this is the filling order. I can rearrange this to numerical order, or the exiting order. So it would be 4f1, 5d1, 6s2. Either of those is fine. And then we go to the electron configuration. You have to watch out with these answers, answers trademark here. You got to watch out because some of these answers are garbage. But let's take a look at this one here. This is the complete electron configuration. I didn't want to do the complete one. Lazy. Here, so up to here is xenon. So we go xenon, 6s2, 5d1, 4f1 in filling order.
So 4f1 should be reversed.
Yeah, if they're going to do it this way, if they're going to do it by n level, then 4f1 should have been written first. Should have been written first, but let's see. Like this. Maybe Quora is a little bit better. I don't know. but they still did it weird. They still did 6s2, 4f1, 5d1. So it's still mixed up. Let's see. Yahoo answered. 6s2, 4f1, 5d1. Yeah, none of these are what I call reliable sources.
What shell would 4F be in?
What shell would 4f be in? It would be in the, let me tell you right here. It would be in the 6th shell. First shell, second shell, third shell, fourth shell, fifth shell, sixth shell. In the 6th shell, I expect 6s2, 4f, 5d. Now, the 5d is kind of weird. You know, it doesn't really matter which one you write first, because what's going to happen is going to be split. So let's do hafnium. If we do hafnium, what is it? Well, hafnium's in the 6th shell, so it's going to be xenon, which would be all the inner shells from there. And then we go on to the 6th shell, it'd be starting off at 6s2. Then we go 5d1, that's 57. And then 58 would be 4f1, 4f2, 4f3, 4f14, fill that. And then come back to 5d1. So it'd be 5d1, 4f14, 5d1. Well, people don't split up the 5ds like that. What they'll do is they'll call it 5d2. And so do you write the 5d first or second? Well, maybe technically it should be after, 5d, so it should really go, if we look at the filling order, it should really go 6s to 4f to 5d, but this one 5d sneaks in there. What is the reason for that? No, there must be some energetic reason for that, Okay. But there. And so if we go to hafnium, you'll see electron configuration with hafnium. Yeah, this here they're doing it like we would have done it. 4, 5, 6. If you're going to rearrange it numerically 4, 5, 6. Otherwise, have it in filling order. If you have it filling order, then it'd be 6s2, 5d1, 4f1, 5d1. You can leave it like that, or you can combine the d's. There, it doesn't really matter which side you combine it.
And then, like, what 4F1, 5D1, 6S2, would those all be considered valence electrons, or would some of
No.
them be considered?
No. Those would not be considered valence electrons. It would be considered like this. We write it like this so we can better differentiate the valence electrons. These would be inner shell electrons here. Their inner shell, even though this is in the 6th shell, they're all in the 6th shell because energetically they're similar, but positionally they're different. Positionally, these 4F are much closer to the nucleus than the 5. It's like in the Bohr orbits. If we look at the Bohr orbits, I didn't spend much time talking about the Bohr orbits, but the Bohr orbits, have some quantum mechanical relevance to them. like the first Bohr orbit, the distance is, no, the distance is like 53, 54 picometers, the first Bohr orbit. This distance has a significance. This is for the 1s orbital. That distance is what we call the most probable distance for the electron in that orbital. And so this actually has a quantum, in quantum mechanics, the Bohr orbit does have significance. The Bohr orbit's like this. You know, we know that in quantum mechanics, we're not talking about orbits, we're talking about orbitals, like this. In an orbital, we have this cloud. It's like the bird's nest. If the nest is in the center, then the bird's most likely not far from the nest. But sometimes the bird will veer far off from the nest. Then we do a little statistical thing on this. The statistical thing that's done is we divide up the space around the nest into rings. And each ring has the same thickness. This would be like onion skin. And so if each layer had the same thickness, then we count the number of dots in each layer. And this is what we see. We see that the volume of the layer grows. And so we can graph this out like this. We can graph out the volume of the layer. We see the volume of the layer grows like this. And then we can see the dot density, or the number of dots per layer. The number of dots per layer shrinks down like this. The farther we go out, the fewer the dots. The most dots are right at the center. The most dots are right at the center, but that volume is tiny. And so when we count the number of dots there aren't that many, whereas these layers out here have more dots, even though the dot density is less. And so what we do is we maximize both those functions. When you maximize both those functions, you get this. You get a little peak here. This little peak here corresponds to having the biggest volume layer with the most dots. And that corresponds to 54 picometers for the first. So when n equals 1, it's 54 picometers. When n equals 2, it's 2 squared times 54 picometers, which we call R0. When n equals 3, it's 3 squared times, this comes from the theory. And so the first orbit's 1 squared, is 1. The second orbit's 4 times. The third orbit's 9 times. The fourth orbit is 16 times the distance from it. And so this is it. This would be 16 times out from the nucleus. This would be 25 times out from the nucleus. This would be 36 times out from the nucleus. And so these ones, being 16 times out from the nucleus, are much closer to the nucleus. However, they all have around the same energy. Therefore, they're in the same energy kind of shell, but they aren't in terms of an oxidizer. If you're an oxidizer coming in to attack it, which electron are you going to attack first? The outermost electrons. That's what we call the valence electrons. The valence electrons are going to be the electrons in the highest n shell. And so the valence electrons are defined like this. The valence electrons are defined as the highest n electrons. N being, what n shell it is. Well, in this case, the highest n is 6. Therefore, any electron in n equals 6 is considered valence. So something like this only has 2 valence electrons. That's it. But what about these? These ones are still susceptible to attack, because if these ones get pulled off, then the next ones in line will be the 5D. This is why we do it numerically. It depends on how strong the oxidizer is. And so these ones get pulled first. So the +2 is very common charge. +2 in the transition elements is extremely common, but it's also common in other species as well, because what would you guess a charge on hafnium is? Let's look at the charge on the hafnium ion. They're thinking. +2. +2 is a charge on hafnium ion, but also +1. So if an oxidizer comes along and it plucks one of these s electrons, that gives us +1. If it plucks off two of these, that gives us +2. So +2 should be common, but it looks like the most common charge on hafnium is +4. Now these aren't considered valence, but these are still susceptible to attack, because once these are gone, then what are we left with? This one. And if we have an oxidizer strong enough, it's going to take the 5d electron. It's +3. If the oxidizer can continue to attack, it's going to take the 4f electron, which is going to be +4. And so not only do we lose this valence electron, but we lose two inner shell electrons in the process. These ones are a lot easier to lose if they're incomplete subshell. If it's a complete subshell, then we wouldn't lose them. For example, if that were 4F14, it wouldn't be touched. And if this were 5D10, it would be hard. It'd have a hard time attacking those. Now we can see that occur in an element that would have that kind of electron configuration. So what element would have that kind of electron configuration where we'd have this filled D and filled F? So let's take a look. Filled D, filled F, we might go to something like lead. Now lead's kind of an interesting one. Let's do the electron. Why don't you tell me what the electron configuration for lead is? Just read it off the periodic table. Okay, good. Xenon. Okay, let's write it down. Xenon. 6s2. 5d10. We should probably do it in order. It goes 5d1 and then 4f14. So, and then we go back and fill it. And so let's do 6s2, 4f14, 5d10. P 2. Yeah, I should scroll up so you can see the rest of the periodic table. You see 6p2? 6p2. Now, what are the valence electrons? Here it's hard to see because this is the filling order. So what we want to do is we